Okay, it's my pleasure to introduce Davide Spriano from Oxford. He's going to talk about hyperbolic models for Castro spaces.
Okay, thank you very much. I will start sharing my screen. Thank you very much for the invitation. Thank you very much for the introduction. Right, so before we start, I want to point out that this is joint work with Harry Petyt and Abdul Zalloum. Please interrupt me at any moment. I believe the talk is going to be slightly shorter than 1 hour, so there is plenty time for questions, should you have some. Okay, so let me start. This is the 2 minutes overview, the elevator pitch of the talk. So there are two very classical, very well-studied objects in geometric group theory, which are mapping class group and Katsir cube complexes. There are many reasons why those are classical and well-studied. There are many applications in the, for instance, in three manifolds, maybe the most important, but in all sorts of areas. But one thing that makes those two objects tractable is that for both of them, we have a very good tool that we can use to study them. Not the only one, of course, there are many, many tools, but one tool that is very important in the study of mapping class groups is the curve graph. And one tool in the case of Katsir cube complexes are hyperplanes. Okay, so out of this picture, there is this picture leaves out the class of Katsir spaces. So Katsir spaces is an overclass. So all Katsir cube complexes belong to Katsir spaces, but this is a larger class. And as it is larger, it is more wild because it contains more pathological examples. And it has been studied classically a lot, but in recent years, we kind of, there have been some progress using, I don't know, for instance, the theory of integral currents, etc., but there are not so many, like the sort of development coming from those two areas it was not really translated to Katsir spaces. And the hope of this talk is to hopefully lay the groundwork for that happening. So that is to say, we are going to want to introduce curve graphs and hyperplanes. And then, of course, we need to prove theorems to really demonstrate that what we introduce is a good analog of those two elements. Okay, so now I will quickly do introduction over those 3 classes. The first one is the mapping class group. So very briefly, let all recall that the mapping class group is you take a surface S just to be safe. Let's say that F is closed, orientable of genus at least 2. The mapping class group is defined as the orientation preserving diffeomorphism of the surface modulo the orientation preserving diffeomorphisms which are in the identity component or that are isotopic to the identity. Right, so the mapping class group is finitely generated group, so it acts on this Cayley graph. Right, but this action is is nice because it's an action on a Cayley graph, so it's geometric, proper and co-bounded, but it doesn't really tell us much because it's very complicated Cayley graph. So what people like is the action of the mapping class group on the curve graph. So the curve graph is hyperbolic. This is a theorem of Mazur-Minsky, and it tells us all sorts of stuff about the mapping class group. I will not really define the curve graph because if you know what it is, great. If you don't know, that's the last time we will talk about it in the talk. It's just motivation. Okay, so this is mapping class group. And now let's tell me about Katsir cube complexes. So what is a Katsir cube complex? Well, it is like a CW complex, a simplicial complex where the cells that you use are cubes. So a cube is just like you take IN, which is the nth power of the real interval 0, 1 to the n with the usual L2 metric. And then you glue them. And you glue them, oops, sorry, too quick, such that faces are surjective isometries. Maybe I should write it. So the gluing maps are surjective so onto faces isometries. So this essentially means that you are not, if this is a 2-dimensional square, you are not allowed to glue another 2-dimensional square like so, because the image of this face, which is just a point, is not surjective onto this other face. It's just covers the interior, or it cannot be an isometry. For instance, I cannot glue like two. This is not allowed because those cubes, cube number 1 and cube number 2, should have the same. They need to be isometric, and they are not in this picture. Okay. And then, so this is what I just told you what is a cube complex, but there is a word Cat0. So a Cat0 cube complex is a cube complex that satisfies two conditions. It needs to be simply connected and satisfy a link condition. I will not define these, but I will tell you what are the consequences. What are the consequences of those two facts? One of the most important consequences is the fact that you can define hyperplanes. So what is a hyperplane? To define a hyperplane, you first need to define mid-cube. So mid-cube, you just take a cube, which remind is just 0, 1 to the power n. And then you restrict one of the coordinates to have one half. So there are if the cube has dimension n, you will have n possible mid-cubes. Here there are 2 drawn in the picture. And then, for instance, now I drew a mid-cube in the example right there, then you propagate. So you see, so this mid-cube intersect this face on a mid-cube as well. In particular, intersect this edge on a point, on a mid-edge. And then there is only one mid-cube of this square that coincides with this mid-cube here onto this edge. So I propagate. That is to say, I keep going, and then here you see there is a branching, and I keep going, etc., etc. So that's a definition of a hyperplane. I can always define them, but if I have those two conditions, the hyperplanes, oh, sorry, here there is another example. I was saying if I have those two conditions, the hyperplane have no self-intersection, they are convex, and they are two-sided. That is to say that they cut the space in two. Right, and this is very good because hyperplanes encode the geometry. So let's make an example. So if I now just look at the distance in the one skeleton, so this is the distance between two vertices, those need to be vertices, in the one skeleton of a Cat0 cube complex. And so in particular, I'm looking at the path distance on the graph. This is the same as the number of hyperplanes that separate x and y. So let's do a proof by example. So I take 2 points here, x and y. I take a shortest path between them. And now I observe every time like this path is composed by edges, and each edge is a mid-cube. So this path will cross a number of hyperplanes that is at most the distance between x and y. And then clearly each hyperplane that separates x and y needs to be crossed. And since hyperplanes are convex, each hyperplane can be crossed exactly one. So each hyperplane needs to cross this path, and this hyperplane that is crossed by that path needs to separate x and y because of convexity. Right. And now let me tell you, I told you about Cat0 cube complexes and hyperplanes, and I'll tell you about Cat0 spaces. So this is a more general definition, and the metric space X is said to be Cat0 if it is geodesic, meaning that between any 2 points there exists a unique shortest path connecting them, and the following holds. So now if I take any 3 points, A, B, and C, so this is X, my Cat0 space. If I take any 3 point A, B, and C, I know that there are geodesics between them because this is the assumption. And then I can look at the quantities, the distance between A and B, the distance between B and C, and A and C. So those are 3 numbers which needs to satisfy the triangular inequality because this is a metric space. So in particular, there exists a triangle in R2, which is Euclidean 2 space, that has the same side length. Okay, and then I just call A bar, B bar, and C bar the vertices of this triangle. Okay, now the condition is the following. If I take any 2 points, X and Y, somewhere on the triangle in the Cat0 space, and if I take the corresponding 2 points, so what would that mean? This would mean the point X bar, such that the distance between X bar and A bar is the same as the distance between X and A. And similarly, you define Y bar. Well, then you compute the distance between x and y in the original space, x bar and y bar in the R2, and the R2 distance, the Euclidean distance, need to be bigger or equal to the Cat0 space. So Cat0 spaces are spaces where triangles are not as big as at most as large as like fat as the one in Euclidean 2 space. Okay. I don't really see your faces. I was trying to see if someone has camera on. So please let me know if you have questions. It's harder on Zoom to know if there are perplexed faces. Okay. I hope that this means that that everything is clear. So right, there are Cat0 spaces and Cat0 cube complexes, which I just showed by CCC. So the spaces are an overclass. Sorry, the other way around. The spaces are an overclass. So there is this containment. But I made this to like sound like a big deal, that there is a big distinction. Is this distinction really big? Well, yes. So there is a theorem of many people starting from Katz-Dahn and then depending, filling in several cases, but uniform lattices in higher rank simple Lie group act geometrically on Cat0 spaces and have T. Okay? But is a theorem of Niblo and Reeves that a group acting geometrically on a Cat0 cube complex does not have T. Okay, so this is a very natural, so uniform lattices in higher rank simple Lie groups is a very natural, very rich class of examples that live in the world of Cat0 spaces, but do not live in the world of cube complexes. Right, so this is the difference between those two spaces. There is really a difference. When we talk about Cat0 spaces, we are really considering a larger class. Okay, so let me go forward. And the goal of today, as we said, is to build those sort of like, to build an analog of the curve graph. That is to say, we need to extract the hyperbolic bits of a Cat0 space. We need to build a hyperbolic model. If we want to do something like with the mapping class group and the curve graph, where we have this hyperbolic space that encodes a lot of the geometry and the algebra. And we want to do this for a general Cat0 space. And our tool, of course, is going to be, so this is the goal, and this is going to be the tool. We want to introduce analogs of hyperplanes for Cat0 spaces. Okay, good. Why do we want to do that? Why this tool is a sensible thing to do if we want to achieve this objective? Well, let's start with a cubical example. So an example from the world of cube complexes. Ta-da! So this is the so-called tree of flat. This can be thought as the Cayley graph of the group Z square with Z, which is also the fundamental group of this thing down here. And also, or you can think of this thing as the universal cover of this torus wedge with a circle. So this is actually a flat. That's how it's called. So all of those are flats, although they are drawn maybe small. You should think that those are infinite flats. And if I now take the lift of these, let's make it blue. If I take the lift of this blue point will lift like a lattice inside this flat, and to each lift you will have a direction which is maybe green, which goes up like so, and then you will have a direction which maybe is red, which goes like so, and then you repeat, and then you will find another flat, etc., and you proceed in a tree-like fashion. Okay, so right, let's clear this up. The goal is we have a space like this. This is a simple but interesting space, and we want to extract the hyperbolic bits. So we want to somehow have a procedure that to this space we associate something hyperbolic. And so now what should we do? What is the what would you do? Like, what is the obvious thing to do? Well, the thing to do is clearly you want to collapse the flats. The flats are an area of non-hyperbolicity. Those are, Euclidean bits, flat bits, so they are not hyperbolic, and so you want to get rid of them. If we collapse the flats, we would get something like an infinite valence tree, because all of, like, if it's all flat now, which is blue, becomes a single vertex, and then I take all of the edges coming out, I will have infinitely many of them, and then this is just going to be the generic vertex. So it's going to be an infinite valence tree. Right, but can I now devise a procedure that does this without knowing what the outcome has to be? So I can look at this picture and I can have an intuition that tells me that the flats are bad, or I know that this is a relatively hyperbolic space, and then I just collapse the peripheral. I want to be slightly like a slightly higher level description. But what if I don't know that? What if my space is not relatively hyperbolic? What if there is not an obvious thing you need to collapse? So I need a procedure that you give a space, then you feed it in this machinery, and then you spits out something hyperbolic. Okay, so let's look at the same example. I made a more cubical schematic. So this is just a smaller bit of this tree of flat. And our goal is going to be, we will take a point here and a point there, and we want to modify the space or measure distances differently, such that the distance between a point here and a point there will be comparable to the distance of the tree. So it will be comparable to this number of edges, and not really by how long, how far away those edges are in a plane. And so this is right. Sorry, maybe I should have said that. It's not clear why this is a cubical example. This is a cubical example because you can endow this picture by a structure of a Katsiri cube complex, so which I try to highlight in this picture here. So you see, you can tessellate the plane by square, and then those would be just like one-dimensional intervals, so one-dimensional cubes, and they can just do this everywhere. And so this is just a selected bit of the previous picture where I highlighted the cubulation. And since I talked hyperplane, let me highlight hyperplanes. So there are three types of hyperplane. There are vertical hyperplanes, which are blue. I drew them only on this bottom plane, but there should be like the same vertical hyperplanes in all of the flats, other planes. Similar, there are horizontal ones, which are those red ones. And then there are, very important, those one-dimensional hyperplanes. So this would be, they correspond to the mid-cube of an edge, which is just a point, but is nevertheless a hyperplane. It's important. It separates the space in two, and it needs to be crossed by any geodesic. So now let's say that I have a point X here and a point Y here. Okay, and I want to define a distance, so some distance, I will call it D0 for some reason, between X and Y. This is going to count some hyperplanes such that, and this is what we need to fill in, and hopefully this number is going to be comparable to 1, 2, 3, 4. It's going to be comparable to 4, and it will not depend on those distances in the flat. Well, so if you never thought about it, think a little bit to try to think of like, what would you do? How would you use hyperplanes to encode such a distance? And the solution to this is the following. You need to introduce the concept of separation. I say that two hyperplanes, H and K hyperplanes, are separated, or to be consistent with notation that we'll arrive later, 0 separated. And this is why there is a 0 here. If they are disjoint, and there is no a third hyperplane T that intersects both. Okay. So now if this is the picture, and I want now to define a distance, which is going to be, okay, changing page, I'm going to define the distance 0 between x and y. We lost x and y. Where were they? X was here and y was here. To be the size of a maximal collection of pairwise separated hyperplanes. Which all of them, each such hyperplane separates x and y. Or let's just call it between to not use the word again. Between x and y. Okay, so how does this collection is not unique, but how could it look? Well, for instance, I will now draw one for you. I will pick one like here, one here. Maybe we can just have different ones. I can have this one. You can have this one. And I can have this one. And then, of course, I need to have all of those ones. Now, the choice of red and blue is not really important. I just need to take any hyperplane that separates this point and that point. Then similarly, now, if you see the collection I drew to you, it is a maximal collection of pairwise separated hyperplanes. Those hyperplanes are disjoint. Let me go back and remind the definition of separation. I need the hyperplanes to be disjoint, and there is no a third hyperplane that intersect both. So there is, given any two on the collection, 1 and 2, they need to be disjoint, and there could not be a hyperplane that intersects both. And you easily see that this is such a collection, and it is maximal. And now you can easily believe that if I use this distance, I will computing this distance this way between x and y is going to be well, essentially twice, like up to an error of maybe +1 or up to an error of 1 or 2, I don't know, is going to be twice the number of those vertical edges between planes, which is exactly what we want. It is comparable to the distance that we obtain if we collapse all of those planes to a point. Right? So this is the idea. And we want to have this idea for general Cat0 spaces, with the caveat, which we don't have hyperplanes. That's going to be the issue. Okay? So now let me go into the main definition of the talk. The main definition of the talk is the definition of curtains. So curtains are going to be, there are other questions. No, hopefully no questions. The main definition is a definition of curtains, and curtains are going to be our analog of hyperplanes. So this is the definition. Let X be a Cat0 space, let gamma be a geodesic, and let P be a unit interval in gamma without the endpoint. So what does it mean? This just means a subsegment of gamma of length 1, and such that this subsegment does not contain the endpoints. Right, so the picture is that this is gamma, and then there is P somewhere of length 1. And then a curtain is the set of point x in x such that the closest point projection of x onto gamma belongs to P. So here is a picture. We are here using the fact that in Cat0 spaces, the closest point projection of a point onto a geodesic is unique. If you are bored and you want to try to prove this from the definition, is not so hard. You can start thinking, okay, well, suppose that I had a geodesic and a point and then 2 closest point projections. This is my Cat0 space. Then I would look at this triangle in R and in R square. Well, essentially, I already almost did the proof of why the closest point projection is unique. You can complete this and find a contradiction. Right, so this is schematic picture. I have a geodesic gamma, I have P, which is my unit length subinterval, which does not contain the endpoints, and then the curtain C are all of the points in the space that closest point project to this interval. Right, and let's also observe that in some sort of analogy with cube complexes, curtain determine 2 half spaces C plus, and C minus, which are the points that project either before or after my segment P. And I put half spaces in quotation because, well, those are not half spaces, because this is a three partition of this. There are three bits of the space. But to some extent, we can call those half spaces with a bit of abuse of notation, like the bits before and the bit after the curtain. Okay. Let me give some examples. So in R2, Euclidean 2 space, curtains are very simple. Those are strips. The closest point projection onto a geodesic are all the points that, well, the form a strips. It's an infinite strip. So here I drew 2 geodesic and 3 curtains that could intersect in some ways. And now let me go back to this example, the tree of flats, the universal cover of a torus wedge to a circle. And now I need to think of it as a cat-zero space. I'm not allowed to think it's a cube complex, so I'm just using each square. I'm using just a normal Euclidean metric. I'm not looking at the one skeleton. So I can take a geodesic like so, and then I can take an interval in that. But then the curtain, well, I understand it very well on the plane is going to be a strip, but then it's also going to contain, well, everything that branches out of this strip. So in particular, this curtain is going to be very big, very, very, very big. It is going to contain inside metric balls of arbitrarily large diameter, etc., etc. So this is just a word of warning. These sort of curtains are significantly less well behaved than hyperplanes in cat-zero cube complexes. Okay. Right. And now let me give you essentially the next two more technical definition of the talk, which hopefully will not be very technical. So the first is a chain. A chain is a collection of curtains such that all of the elements are disjoint, and this happens and this does not happen, meaning that if I look at the half spaces that we defined before, they form a chain under inclusion with the usual meaning of chain. So for instance, if I orient them like so, and I look at the half spaces, those form a chain under inclusion. This is, if the chain is finite, this is the same of requiring that they all separate 2 points. And the picture we do not want to have is something like that. So this is a forbidden picture. You see the half space do not form a chain under inclusion, because if I orient them like this, for instance, or maybe I orient this one like this one like that, and then there is no way that I can orient these 2 half spaces to form a chain under inclusion. So this is a chain. And then before, if you remember, we talked about hyperplanes, and there was a notion of separation. We said the 2 hyperplanes are separated if they are disjoint and they are not crossed by another hyperplane. And we have the analog, which just we need to introduce a parameter. We said that the chain is L separated, where L is just a parameter. You can pick any natural number. If whenever you take 2 elements in the chain, 2 curtains in the chain Ci and Cj, every other chain that intersect both its size at most L. So picture in R2, if I take 2 chains, 2 curtains C1 and C2 that are disjoint, that is to say 2 parallel strips, those are never going to be L separated, because I can always say take a sequence of other parallel strips that intersect both, all of them. Whereas it might happen in other spaces that they have C1 and C2 to be 2 curtains, and then whenever I have a chain that intersects both, the size of this chain is bounded. Okay, so this is the definition. This is a L-separated chain. Are there questions?
I just want to let you know that you can move the little window off the screen. You can just...
This one?
Yes, just slide it all the way to the right, say.
Oh,
sorry.
So, if I do, okay.
There you go.
Thank you. Okay, I was unsure if the little window would appear only on my screen or also in the shared one. Anyway,
yeah, we lost your video.
Natalia.
You're welcome.
Oh, okay, yeah. Good, but you can still see the screen, right?
Yes, I can.
Good, good, good. Okay. Right. So this is about separation. Let me. This is a remark for the experts that know what a space with walls is. So curtains do not form a space with walls. A space with walls meaning that you cannot use Sagiv cubulation. So of course we are not proving. You cannot use curtains to prove that all Cat0 spaces are cubulated because it is not true. We just discussed that there are groups that act geometrically on Cat0 spaces that cannot act geometrically on Cat0 cube complexes. And the reason why they do not form a space with walls is that you have too many curtains between 2 points. So if I have a curtain, I can naturally decide now a real definition of half spaces, like a partition of the space in 2. I just decided, for instance, this curtain belongs to this bit on the right. So I take this whole thing as a half space, and this one is another one. This would be a wall. But then if I have 2 points, and I don't know, I just take a geodesic between them, and I can easily fit infinitely many half spaces determined by curtain by just sliding the curtain by some very small real number. Okay, right. However, again, this is just maybe so. This was for the expert. So maybe if you never saw a space with wall, the takeaway is that between 2 points you can fit many curtains. But if I take a chain instead of just considering curtains, the size of a chain is finite. Why is it so? Well, suppose that I have 2 points here, and I have a chain between them, which I just drew. The important thing is that those curtains need to be disjoint. Good. Now I take a geodesic between this first point and this second point, and this geodesic will have a first entry and last exit point from each of those chains. And now if I zoom in, I just take P and Q to be the first entry and last exit points, and I closest point project them onto this segment that is used to define the curtain. And the fact is that projection onto geodesics does not increase distance. This is a fact of Cat0 spaces. So the distance between P and Q needs to be at least 1 because it cannot increase. And so each time I cross a curtain, I need to spend at least 1. And since the distance between my endpoints is finite, I can only fit so many disjoint curtains between them. Right? So that's nice. So this makes the thing slightly more tractable. And now I have all of the definitions. All of the motivation. Let me actually finally define the model. Given L, which is a natural number, define the L distance between 2 points in my Cat0 space X and Y to be the size of the maximal L chain separating them plus 1. Don't forget, or 0 if X equal Y. Right? Don't think too much about the plus 1. This is essentially a technical artifact that is needed to make triangular inequality work. The important bit is this one. So you essentially measure how many, what's the biggest size of an L chain you can fit between 2 points. So if you think of the analogy with hyperplanes, this really covered the case of the trio flats. And the theorem, which is, again, the name of my talk co-authors are Petyt and A Zalloum, is that this function is a metric. The space that you obtain by having the same set, but this metric is hyperbolic, and the metric is equivariant. So every isometry of your original space induces an isometry of this new curtain model. Okay, so this is good. After all of this motivation, we finally managed to get to this model. So this is this hyperbolic model. But I said a model, this is a plural. So those we have many hyperbolic models. Given L, we have so we have 1 for each natural number. So we have an infinite sequence of hyperbolic models, and they will have in theory, different characteristics. Some of them, are going to be different than the others. And so the natural question is this. So this is very impressive, but can you do it with only 1 space? can you somehow manage to combine all of this information? And well, what are the issues? The issue is this. So if I call x1, let's just remember x1 is the space x equipped with the distance d1, choosing the separation constant to be 1. If I just take the identity map, because those have all different distance but the same set, so the identity map is a map. Right, the map is identity, and you just say the distance. We have a sequence of maps like that. And what do I mean with this? I mean that those maps are Lipschitz, are distance and increasing. In fact, if I recall, this is just recall the definition, fixed an L, I define the L to be the size of the maximal L chain. And since an L chain, being an L chain is a stronger requirement than being an L+1 chain, it always happens that any L chain that separates x+1 is just by definition an L+1 chain. So the distance is satisfies this inequality. So those spaces get bigger and bigger and bigger. And you can start hoping that you have some sort of like obvious limiting procedure. But the first is like, you might expect those to eventually stabilize, but they don't. It might happen that those spaces just keep changing and changing. So you cannot like expect that eventually they are always the same space. If I try to define a distance to take the limit as L going to infinity of these spaces, you can do that. That is a perfectly acceptable thing to do. But you will not, in general, end up with a hyperbolic space. You will end up with a space that is not hyperbolic, and also maybe not the spaces you started with, and so it's not really good. And why is it true? Well, the intuitive idea is that each of those spaces is slightly less draconian in what is allowed. So in the first space, you really just look very hyperbolic behavior. In the second space, you allow slightly less hyperbolic behavior, and so on and so on. And so you see more, because in this one, you just kill everything that is not very hyperbolic looking. And then you see more and more. So all of those are hyperbolic, but with worse and worse and worse constants. Like the triangles get fatter and fatter and fatter. And then in the limit, the triangle just becomes like in principle, you might just get something that is not hyperbolic. So the last approach you can think about is you can rescale them. So each of them is hyperbolic based on different constants. If I rescale the metric, they will all be uniformly hyperbolic. But then if I do that, I get a bounded space, because I shrink and shrink and shrink and shrink to make sure that my things that I want them to be hyperbolic are hyperbolic. But then by doing that, essentially any 2 points, no matter how far they are, eventually I will crash them together. So I will get no meaningful information out of that. So none of those three obvious approach works. So you need to do something different. And here's the idea. The idea is actually very simple. I recently learned that this thing is called a convex combination of distances. What is to say, I pick a sequence of positive coefficient that sum to 1. This is actually not very important. It's just important that this quantity is finite. And I define a new distance, the capital D, to just be, you take the L distance and you multiply the coefficient. And you do it for all the L. And the fact that this sum converges guarantees you that this quantity is going to be finite. And the theorem, again, is that this function is a metric, this space is hyperbolic, and each isometry of your original space is an isometry of the new space. Okay? So I'm almost at the end. This is how you define these spaces. And now let me finally, I spent a lot of time in the construction. Let me finally tell you some theorems. Why are those day spaces good? Like, I never told you yet that these spaces are not bounded. If I would always get a bounded space, this would be really disappointing. But that's not the case. And the theorem are the following. The first theorem is that suppose that I have a group G acting on a Katsir space semi-simply. And this is really not an important hypothesis, by the way. If you don't know what it means, you can ignore it. G, an element G in G, given an element G in G, the following are equivalent. G is rank 1, or if you don't know what rank 1 means, so rank 1 means that G as an axis is an isometry, and this axis does not bound a half flat. So it does not happen that this is the axis of G, and here there is a Euclidean half flat. Either these happen, and again, If you never heard, this is the equivalent for a Cat-0 space of G being Morse, if you know what this means, or G being contracting, again, if you know. And this is really, again, also for the expert, this is why we use the word semi-simply. If we were not using that word, you would have the word contracting here. It's just slightly less well-known concept, I guess, maybe not. So the following are equivalent, G is rank 1. And now I started saying that there are analogy with the mapping class group. So where are they? Well, in the mapping class group, I have the mapping class is pseudo-Nosov, which is the analog of being contracting, if and only if the orbit, like phi, has quasi-symmetrically embedded orbit in the curve graph. Oops, I missed a parenthesis. This is the theorem of Mazur-Minsky. And while we have exactly the same result, an element is rank 1 if and only if the orbit map to XD is a quasi-symmetric embedding. And what about, and in particular, this tells you that if this XD is unbounded, sorry, if you have a rank 1 isometry, then this has to be an unbounded space because you need to be able to quasi-symmetric embed a line into it. And then let me give you another analogy in Cat-0 cube complexes. G is rank 1 if and only if G skewers two separated hyperplanes. So skewers means that there are C1 and C2, which are separated, so in particular disjoint, and G moves C1 behind C2, like that. And to be precise, I need to also have the orientation doing that, but that's not a big deal. This is a theorem of Capra-Sagiv. And while we have exactly the same result, so this is the same, if and only, sorry, those are, G is rank 1, if and only if there exists some L, such as G skewers two L separated curtains. And I already mentioned about this before, something about this. A corollary is that if G acts on X semi-simply, then you have a rank 1 element, if and only if XD is unbounded. So before I told you that if you have a rank 1 element, then this has to be unbounded, otherwise you couldn't have a QI embedding. But then you think about Gromov classification of action in hyperbolic spaces, and it says that if you act co-boundedly in a hyperbolic space, oh, that's right. Sorry, this is as was stated, this is wrong. You also need co-boundedly. That's co-boundedly. I'm always, to be honest, I'm always thinking of group acting properly co-compactly on a Cat-0 space. That's what I have in my mind. So this sort of hypothesis is, but I need to state it, otherwise the theorem is not true. If I have a group G that acts on a Cat-0 space semi-simply, then you have a rank 1 element if and only if XD is unbounded. And this is the other direction. If XD is unbounded, then the Gromov classification of isometries tells you that there needs to be a rank 1 element, and then you show that this rank 1 element, this rank 1 element, sorry, I mixed my word. If XD is unbounded and G acts on it, then G needs to act by a loxodromic element. That's the word I wanted to use because of Gromov classification. And then you use this equivalent to show that this loxodromic has to be a rank 1 isometry of X. Sorry for the confusion. Okay, this is good. Can we say more? Yes, another very interesting application that we had, this actually was our original motivation, is the following, is that if you have a group G acting on X geometrically, then exactly one holds. Either G is a rank 1 element, which implies that G is virtually cyclic cylindrically hyperbolic. This implication was well known. Or, and this is really, our contribution is the fact that those are the only two options, not in those implications. Or G has linear divergence, if you know what it means, which means that there's no cut point in an asymptotic cone. That is to say that G is wide. I will not define what an asymptotic cone is. Intuitively is you look at your space from very far away. And if you have a rank 1 element, then this needs to be a cut point in your asymptotic cone. But it is not clear at all if you have a cut point that it has to come from a rank 1 element. And essentially, this is what we prove. And just a remark, after we proved this theorem, we realized that this was already proved by Russell Ricks somewhere in a paper that, I think they didn't even put it in the introduction, so it was very hard to find. But we found it. So this is, but they use completely a very different technique. They did ultra limits of asymptotic cones, ultra product of asymptotic cones, whereas this is a more hands-on construction because you use this set of curtains. And let me tell you one final application is that an analog of Ivanov's theorem. So suppose that you have X that is a proper Katsira space, proper Katsira spaces with the geodesic extension property. So this means that every geodesic segment can be extended to a bi-infinite geodesic. And now we need some hypotheses. And those hypotheses are going to be very not restrictive. So either you have a geometric action by a group that is not virtually free. So any Katsira space with a co-bounded and proper group action that is not a virtually free group works, or X is a tree of valence at least 3. So this is also fine if you have a free group, or X is one-ended and there is no assumption on the group action whatsoever. Suppose that you have one of those 3. Then the isometry group of X is the isometry group of XD. So we said that this was true. Every isometry, the construction was equivariant. So every isometry of your original space induces an isometry when you take the curtain distance. But the theorem is that it's the opposite. Whenever you have an isometry of this weird, mysterious hyperbolic space, this necessarily has to come from an isometry of your original Katsira space. And this is the last thing I wanted to tell you. I thank you very much for your attention.
Okay, thank you very much, Davide, for giving us a great talk despite being sick. Okay, do you guys have any questions for Davide?